finally, I'm switching away from filtration. You may have gotten the impression that I could have talked about filtration forever, and that's probably true. Because to be completely fair, we still haven't delved into nearly all of the details that go into designing one of those stack rapid sand filters. But we got to call it quits at some point. So today, I want to talk about something that might just sound totally boring, but I want to assure you this is not. Inlet and outlet manifolds, so pipes that have maybe multiple holes in them that we use to get water into a tank or out of a tank. Obviously, this is happening inside the clarifier, but it's also happening inside the filter. And we want to think about how does that work? And the reason that I really wanted to cover this is because problems with manifold design and more generally in getting the water to do what you want it to do are very commonplace. It is very common in water treatment plants for the water not to do what the designer hoped it would do. And there are still clarifiers, sedimentation tanks being built that don't work as intended because the water doesn't do what the designer was hoping. And certainly there are filter failures because of lack of a good flow distribution. So I want to introduce you to why that's an issue and kind of what makes it complicated and what some of the really big ideas are. I'm going to try to avoid going through all the equations, because I feel like that doesn't connect very well, but there is a chapter in the textbook that you can use for resources if, as you go out in your career, if you run into this issue of how do you get uniform flow distribution between multiple paths, come to the textbook. There's at least some good guidance there. And oh goodness, and we end with in which change in kinetic energy becomes significant. Thanks to the writer of Winnie the Pooh, because kinetic energy shows up in a surprising way in this problem, and hopefully we'll enter that today. So some more context. Remember Agalteca? I'll show you some pictures to remind you of that problem. And just this insight that water treatment plants commonly have processes where flow divides into many, many parallel paths, and I'll show you where that's happening in an agua clara plant. And it is very easy to have poor performance because the flow isn't dividing the way you might have hoped it would. So this is a reminder of Agalteca. Remember, we built this plant. This was the clarifier, and we had a problem with flocks coming up at the end of the clarifier. And it turned out that the problem was related to water having a velocity component that we weren't expecting, and that causing a mean flow of water towards the end of the clarifier. I want to point out that I just, on Monday, I spoke with one of my former students who's working at the Cornell University water filtration plant. And over spring break, Cornell water treatment plant shuts half of itself down, and they operate longer hours to make sure they can still deliver enough water, but demand is down because the students are gone. And they have a large horizontal flow sedimentation tank, and it accumulates sludge over the course of 6 months. And so my former student was in there helping to clean out that sedimentation tank, and he showed me some photos, and he showed me that in that sedimentation tank, the outlet used to be right at the end of this horizontal tank. And then at some point, there was a retrofit and it was moved back about, I don't know, maybe 10 feet or something. And so it's no longer at the end of the tank. Now, I don't know for sure why that happened, but I have a very good guess. And my good guess is that they discovered that all the flocks were coming up at the end of the tank. because the water is flowing horizontally down through this tank, and it all comes up at the very end, and it lifts a bunch of flocks up from the bottom right at that point. And so the end of a sedimentation tank, a horizontal sedimentation tank, is a bad place to collect what you thought was going to be clarified water. So this is just another example of water not doing what you might have first expected. And then, okay, how many places in a plant do we have multiple paths where the water can go? And we're hoping that it divides equally between those paths. So there are many places, and I'll show you some of them. And you can think about, why is this important? Like, if all of the water went through one clarifier bay instead of divided equally between the 4 that I've shown you, then you'd have 3/4 of the plant not doing anything, and your plant would not perform well. And the insight is, the water will not divide equally. There will always be something that makes it not be perfect. And so we're going to be trying to figure out, how do we minimize those imperfections? So here's some places where there are parallel flow. So in the clarifier, in this design, there are 4 clarifier bays. So we want the water to distribute uniformly and flow in parallel through those 4 bays. In each bay, there are something like, how many? Something like 50 or 100, no, 100, something like 100 diffusers that are pointing down into the bottom of the tank. And we would like the same flow out of each of those diffusers. There are plate settlers, and we would like the same flow between going through each plate settler. And if we go to the filter, in this case, we had 2 filters, so we like the flow to divide equally between those 2 filters. There are filter layers. We like it to divide equally between those filter layers. There are branches in the filter layers. We want the flow to divide equally between the branches. And finally, we want it to divide equally between the slots in the branches. So do you see how fine this got? Like, there's so many places where we're assuming that the water is going to just uniformly divide between these multiple paths and everything will be fine. So this is like a review of hydraulics or fluid mechanics. So let's think about, how does this clarifier work? And specifically, why does water move through the clarifier? Where does the energy come from that's pushing the water through these clarifier bays? So let's look at an elevation view of the end of this. So I'm looking at those channels that are dividing the water between the clarifier and, oh, maybe I realize I look at these drawings and I know exactly what's happening because I've been staring at them for 15 years and you've been staring at them for 3 months. So let's just review. Water's coming in this inlet channel, going down through these 5 inlet ports that go to inlet manifolds. It then goes down through the diffusers, around the jet reverser, up through the flock filter, up through the plate settlers, and then into this outlet manifold along the top of the clarifier, out this port, and then it's into this little channel, and that channel has a weir, and it flows over that weir and drops into a channel where it then exits and somehow magically gets to the filters. So the water enters in this channel, and as far as the clarifier is concerned, it's exiting again in the channel that's right next to the clarifier bays. So the question is, what pushes the water from this inlet channel to this outlet channel? So let's look at an elevation view showing what the water levels are. And there's too many things going on, but the blue lines over here point to the water level in the inlet channel. That's the same as the outlet level of the flocculator. Okay, and you also see something interesting, that this inlet channel has a change in elevation. The bottom keeps on coming up as the water goes downstream in that channel. Okay, so that's the water level in that inlet channel. And then over here is the water level in the clarifier bay. So remember, the water goes from this inlet channel, it goes down through an inlet pipe, up through through the diffusers, up through the plate settlers, and ends up at this water level, which is here as well. And then ultimately it goes out through the outlet manifold and goes to this outlet channel. And we see, oh, there's a big change in elevation. Well, big, a small, like 5 centimeter change in elevation between the water level in the clarifier bay and what it is in this outlet channel. So here's my question. Where is the majority of the head loss in the clarifier bay? And this is like a mystery, and I'll guide you through it because it's not trivial. So we have these clues here that are telling us what's going on. And look, if we take the water level that is in the inlet channel and extend that over, we see that the water level inside the clarifier bay is almost exactly, or maybe is exactly the same as the level in the inlet channel. That means that there's almost no head loss, almost no pressure drop, or almost no energy loss between the inlet channel and getting into the top of the clarifier bay. And that's true. And there's a good reason why that's true. And it's related to the fact that, okay, we know, you might remember that plate settlers have almost no head loss. Like the flow is really slow. The shear on those plates is just tiny, tiny, tiny. The head loss is measured in a few micrometers, which is a ridiculous unit of head loss. So there's no head loss in the plate settlers. But what about the inlet manifold and the diffusers? Why is there no head loss there? Well, what does the inlet manifold and the diffusers, what do they carry? They're carrying flocculated water. And you know that flocks are really wimpy. They're super fragile. And that means that we have to handle them very gently, otherwise we break them. And so if we did have significant head loss in the inlet manifolds or in the diffusers, that would break the flocks, and that's a problem. And so that's why there's almost no measurable head loss. I'd have to go back and look. It's probably order a millimeter, about a millimeter of head loss between the inlet manifold and getting it into the clarifier bay. So that's why that last blue line, that's why that line is horizontal, why there's no significant change in elevation between what's in the inlet channel and what's inside the clarifier bay. So water can get between those 2 points by going through pipes and diffusers and plate settlers, and there's no significant head loss. But then look, there's this big difference in water level between the clarifier bay and the outlet channel. So can anybody figure out where's all that head loss happening? There's a big elevation difference between the water in the clarifier bay and where it comes out of the outlet manifold into the outlet channel. Where did all that energy get? We're looking for something that would cause head loss between where the water is in the clarifier bay and then it exits by going through these holes. There's little orifices, you can just barely see the outline of it, orifices in the outlet manifold, and then flowing through that outlet manifold and getting to this channel. Where might there be head loss? It's going through holes, and then after the holes, there's an expansion, and that is indeed the case. And how would you characterize those holes? Like, if you think back to early in the course, what are those holes? What did we call them? Because we had an equation to describe this. Oh, this is completely unfair. Monroe's asking you questions about like the second week of class. Oof, it was an orifice. And there's head loss for exactly the reason that Dan mentioned. There's a flow expansion. And so the kinetic energy that the water has when it's going through the contraction in the orifice largely gets lost as it's flowing into the pipe. And so we lose energy there. And so that's one place where there could be head loss. The other place that there could be head loss is just like major or minor losses in the pipe itself. There is a minor loss. That pipe does exit into the channel. And so right here, there could be an exit loss. And it turns out that the major and minor losses in that pipe are actually really tiny as well. It's the orifices that are causing the majority of the head loss. And then that raises the question of, well, if we in general, we try to save energy going through the plant because all the elevation drops that we have force us to build a taller building. So it costs us money. So the question is, why is there 5 centimeters of head loss there? So you can hold that as a puzzle. Like, why didn't we just drill bigger orifices? We could have easily done that, right? It would be trivial to make the holes in the pipe bigger. So why did we intentionally make there be 5 centimeters of head loss there? So it is those 5 centimeters of potential energy difference that's pushing the water through the bay and specifically through the outlet orifices. That's how it happens. And just as a reminder of, this is what it looks like when there's water flowing. So this channel has flocculated water. There are the clarifier bays. Here are the effluent manifolds that are dumping water into this outlet channel. And then it's flowing over that weir like a waterfall and into this channel that then is somehow connected to the filters. So what is different about the path of water through the clarifier bays? Does the water have to take, is there any difference in the path that the water has to take to get through these various clarifier bays? Because if there are any differences, that could cause a difference in flow through the different bays. So do you see any difference in the path through these various bays? Yeah, Hannah, what do you see?
They're different sizes.
The bays look like they're different sizes.
Well, I guess not. I guess I was thinking more vertically, like those are different sizes, but like the tubes aren't lined up either, like on either side of the numbers.
Okay, so this is confusing. These tubes, this one is sensor access to flock hopper. So it's just a way to shine a light down there or drop a flashlight in, and that's submersible, and see when you can't see it anymore because it got submerged in the sludge. So that's what that tube is for. And this one is a tube that we no longer use, that was used for allowing us to dump water from the very top of the sediment of the clarifiers. The inlet or the outlet manifolds are placed, in the middle of each clarifier bay. They're identical, but there is a difference in the path that the water has to take to get through the various clarifiers. Because, okay, the flocculator is actually at the bottom of the page off the screen. The water is flowing up in this photo. And that means that to get through clarifier 1, it's a shorter path, and to get through clarifiers 5 and 6, it's a much longer path. So the question is, does that cause us a problem? And it potentially does. And I'll come back to eventually how that might cause a difference in flows, because there's a surprising answer to why it causes a difference. It's just another view of the same thing, just to remind you, okay, we can draw this in Onshape, or we can take a picture of the real thing, and they look very, very different. And just this, notice the sloped bottom. in the inlet channel, and think about the fact that it costs us money to make that bottom of the channel be sloped. We have to use extra concrete. So that's another thing that we must be doing for a reason. Just to ponder, like, why do we care about that?